All right, let's start with an easy thing. What's the derivative? This one's simple. No major concepts with this one. Okay. 6 is gone, right? Okay. How do you go backwards? How do I undo what I just did? Don't worry, you're not supposed to know the answer to that question. It's known as an antiderivative, or what you're typically going to be referring to it as is integration. So with everything in math, we have the inverse. We have to be able to undo what we've just done. So in derivatives, we have to be able to go take a derivative and go back to the original function. Okay, so that would be known as the integral. And you'll typically see it as this symbol there. It's that little S symbol. It's actually because it's an elongated S, which because it's actually a summation of a whole bunch of rectangles underneath the curve. So integration actually will give you the area underneath the curve, which you'll get into at the beginning of Calc 2, where you're actually looking at area under the curve and whatnot. All right, so that's that. It can be called the antiderivative, but typically we call it the integral. Section 4.9 is actually called the antiderivatives, and then section 5 or chapter 5 starts calling integration. So, all right, so let's look at this simple one. Let's look at the 5x to the third. We take the derivative, and it goes to 15x squared. And we do that, so x to the n, and it becomes n times x to the n minus 1, right? So if I want to go from this back to that, so if that was x to the n, what do I have to do to the exponent? What am I doing to the exponent if I'm starting off with 2 and I'm going back to 3? It's going to be n plus 1, right? Mm-hmm. Because we have the n out here, right? But I want to be able to get rid of that. So that's really n plus 1. So make this a little bigger. So instead of multiplying by the piece to go backwards, we're actually dividing by that n plus 1. So that's your first rule. Did I write it nicely on the next screen? I did not. We're going to. So the integral power rule is x to the n, x to the n equals x to the n plus 1 over n plus 1. Just as with everything else, that's one that's going to come back quite often and be used a lot. So let's use it on a few. So 10x squared. What would be the integral of 10x squared? So we can ignore the 10 for a second because it's just a constant, just like we were doing with derivatives, the coefficients can stay off by itself. So what's the integral of x squared? If n was 2, we're going to go backwards, right? X to the third divided by 3. So this would be 10 thirds x to the third. What about 5x to the 0 power? So again, we can ignore the 5. Huh? Yeah, it's x to the first over 1, right? Which, yes, would just be 5x. Now, there's it's like, why do we even care? However, this one's important. What's x to the 0 power? 1. So that's really not even there. Normally, you're not going to see that there. So the integral of 5 is 5x. So when you have the integral of a constant, you actually are putting that x back onto it. And if you think about it, what was the derivative of 5x? It was just 5. So when you had the derivative, when it was just the x disappeared. So the integration just puts it back. Okay. So x to the 0 just allows you to see that concept. But normally you're going to see it as just 5. That makes sense? Awesome. All right. Not this one. If this was a derivative, what have we always done? What do we do? Yeah. Yeah, we put it up and made it negative, and we use the power rule, right? Let's do the same thing. So we're going to do the integral of x to the negative second power. All right. So that's going to be what? X to the what power? Negative 1 divided by negative 1. So it's going to be negative 1 over x. All right. Try the last one. And don't say the answer out loud once you get it. And don't say the answer out loud if you get totally confused. So what do we get? Huh? So the rule, I get x to the 0 over 0, right? Which doesn't work. What's the what derivative gives me 1 over x? Huh? ln of x. So that doesn't work. This equals ln of x. And it's the absolute value of it. Because in this problem here, any x will work except for 0. So we need to have that in respect to the final answer too. That's why if you realize the very first question had ln of absolute value of x on purpose, because I wanted you to see that derivative. Okay. All right. So we covered that one and that one. What's the integral of e to the x? E to the x. All right, those are always going to be the same. That's one of the nice things. The derivative v to the x is c to the x. The integral v to the x is e to the x. What else? What's something else? What's something? What disappears when I'm doing my derivative? A constant. So how do I get that back? Because I'd want the original answer back, right? So when we take the integral of a function, we're going to go backwards. However, when I take the derivative, I lose information. So somehow I have to put that information back. Most situations, we're not going to know what that information is. So if we're just doing a simple integral like this, what was that? Like that, we just put a plus c at the end. Because I don't know what that information is, but I know a constant could have been lost. That constant could have been 0. Like there might not have been a number there, but that's okay. C can be anything. So because I lose information, I need to put something that says there's some information lost. Here it is. Some of the problems that we're going to do today, we're going to actually figure those numbers out to be able to get them. But in a lot of situations, you are not. So the number one thing that most students forget in Calc 2 is they'll forget the plus c at the end of their integrals. Whenever you're doing just a standard integral, you need a plus c. So don't forget your plus c's. All right. Here is this wonderful table. All right, so this is the table very similar to what our derivative tables were. Your constants, we can just pull those out. Just like I did with the 10 and the 5, I can pull those out, ignore them, do the problem, and then put them back in there. Addition still works. So addition and subtraction, I can still do the integrals of each of the pieces individually, and we're fine. That's the power rule we just talked about, the 1 over x to the ln of x we just talked about, e to the x. The b to the x ends up being b to the x over ln of b. We've done that one. So if you noticed, it's basically just the opposites. Cosine becomes sine. Sine becomes negative cosine. It's going backwards. So one of the things that's really confusing is this. So we have, in derivatives, we have sine of x goes to cosine of x, goes to negative sine of x, goes to negative cosine of x, and then it goes back, right? And it just keeps repeating itself. So that way is the derivative. That way is the integral. So sine of x becomes negative cosine of x. Cosine of x becomes sine of x. So it's the opposite direction. Another one that's very easy to screw up because it's very similar. It's just the opposite direction. And sometimes it's literally just a sign change. Like sine of x goes to cosine of x in derivatives, but it goes to negative cosine of x in integration. So it's really easy to make those little mistakes. Now, a couple other ones. Remember we had secant of x is secant tangent. So secant tangent is secant of x. The hyperbolic ones we're probably not going to see very often, so you don't really need to know those two. These you do need to know, though. These do come up quite often. So I would definitely have those written down. Pretty much anything, if you have the rule going one direction, you can go backwards in that same thing. Okay, that's the concept of the anti-differentiation. It's just literally going backwards from it. Not everything works easily going backwards, though. As with any kind of thing of going backwards, this doesn't always work out nicely. So when we're looking at, say, like multiplication, we had a rule, product rule, right? There is a corresponding rule in integration, which you're going to learn next year in Calc 2, or next semester in Calc 2, or when you take Calc 2. it's called integration by parts. That does that. So the quotient rule becomes partial fractions. There's rules for all those. Some of them are a lot more complicated than this. And that's why we spend an entire semester doing Calc 2. Calc 2 is all integration. That's literally what you learn in Calc 2 is integration and then some series towards the end. And then Calc 3 is doing all the same stuff, just in 3 dimensions instead of 2. Which is why you don't need that for biology or any of the science classes. Engineering stuff, yeah. So, all right. So let's look at some. So see how it says find all functions of G? That means that plus C, because there's multiple functions that we're going to get out of it. That plus C basically gives me a family of functions, because C could be anything. All right, since it's addition, I can do this in pieces. So we're going to find the integral of 4 sine x. So what is the integral of 4 sine x? Remember, the 4 I can ignore. Yeah, what is it? Negative cosine x. So negative 4 cosine x. All right, so next, what am I going to do with this? This is even more important now because you do not have a rule to know how to do this as a quotient. Okay? So if you think back to the original problem when we first started, before I taught you the quotient rule, how did I show you to do fractions? What can I do to any fraction? I can split it up and put the denominator in each piece. So this becomes 2x to the 5th over x minus this x. I'm going to change this to x to the 1/2 over x. So I get 2x to the 4th minus x to the negative 1/2. And I will tell you right now, if you can avoid doing a quotient integration, you want to avoid it, even after you learn the rule, because the partial fractions rule is the hardest one. You do not want to do that if you don't have to. If you look, so I'll show you because it's actually kind of funny. I don't know. Do they not have an index? Oh, they don't have it in the book? Oh, they don't have it in the online book. Oh, that's not fun. All right, I'll do it this way. So when we're looking at derivative rules, you basically have, right, these, right, the simple rules, and then there's some ones that you kind of like memorize type things, but that's basically it. Okay. Huh? Oh, those are probably all fit. I would not write those all down on the note card. Nope, that's not the one I want. Here's what I wanted. Here is the tables of integration. There's 112 of them listed in 4 pages. Huh? Uh-huh. All right. There's that many because going backwards is harder. So there is a ton of them. You are not going to want to memorize them all. When you're going through in Calc 2, you're going to learn rules that'll actually be able to help you find a lot of those. But I will tell you, this is where memorizing those basic derivative rules and those basic derivative functions are so important because they're going to help you solve a lot of the really easy ones. And when we look at what's known as the U substitution, which is the inverse of the chain rule, you still need the derivatives. So while, yes, you can use an index card and stuff like that, you really truly need to memorize those basic derivative rules. Okay, don't just sit there and write them down and use them constantly. You're going to need to know those down by heart to be able to really succeed well in Calc 2. Remember I said in Calc 1, if you don't know pre-calc, you're kind of screwed. You're still kind of screwed in Calc 2 if you don't know pre-calc, but on top of it, if you don't really remember the derivative rules, it's just going to compound, and it's going to make your life a lot more difficult. So it's like in little things like this, being able to simplify the problems down, like those are going to make your life easier. So you don't have to do a more complex way to solve the problem. And then sometimes you're going to do this complex way to solve a problem and you're just going to go in circles and you're going to get stuck because a simple algebra step would have gotten you out of that. So, all right. So we're now at this, right? So I can find the derivative of that or the integral of that. So let's do the integral of 2x to the 4th. We have what? 2x to the 5th over 5. So 2/5 x to the 5th. What about negative x to the negative 1/2? How'd you get negative 2/3?
Because
Oh, you're
negative 1, and then since it's one of fraction.
you added 1 wrong.
Oh,
I'm like, wait a second. Yes, that's right. If it was positive, that's okay. Honestly, these are the little mistakes you're gonna make. It's like it's little stupid little things like that that it's like, oh, like yeah. So we got the negative sign. The other thing that's really, really common to make, and I make it all the time, is you forget you have to add 1 before you bring it down. Okay, because in derivatives, you bring it down, then you subtract 1. In integration, you have to add the 1 and then bring that number down. So it's like, you'll see me off a lot. I do this, like that'll be a 4 instead. Because I moved it and then added the 1. So it's like, make sure you do it in the correct order. So I'm adding 1, so this becomes x to the 1/2 over 1/2. So that becomes negative 2 x to the 1/2, or negative 2 squared of x. And just like we started with the derivatives, doing them in pieces will help you. Okay. We're not going to get into any of the multiplication ones. We're not going to get into any of the division ones. It's all going to be addition and subtraction problems. Okay. We will do some where there's a function inside of a function at the end when we look at U substitution, but that's about as more complicated as we get. And that's not very complicated as compared to some of the other things. So it's going to be a lot of things where you can literally split it up and look at it in pieces. So now we have to do the last thing. We have to put it all back together. So g of x, because we did the integral of the derivative, is negative 4 cosine of x plus 2/5 x to the 5th minus 2 squared of x plus, don't forget the plus c. All right, questions with that one? Just lots of little things. All right, let's look at this one. All right, you'll notice that I added that to it. If you remember when we were doing derivatives, one of the formats you saw was d over dx. Basically just tells you what you're taking the derivative of. Same concept here. That dx at the end tells you what you're taking the integral of. So we're doing this in terms of x. And this stuff, it doesn't really make much of a difference because it's all going to be one variable. However, it does make a difference later on. And when you did the homework and stuff like that, there was actually some problems where you were taking the derivative of, I think one of the problems was with the derivative of n, but there was a k in there. K was considered to be a constant. You weren't using that value there. And when we looked at doing implicit differentiation, remember we were doing the derivative of the x in terms of the y and those type of things. So that can actually have some impact on when you're doing things. So the proper way to write it, you'll see the integral of e to the x dx, or the integral of whatever it is, dx at the end, or dy if we're doing it in terms of y. So what's the integral of e to the x? Just e to the x. All right, so what's the integral of this? We can pull the 20 out. So I can rewrite this as 20. 1 plus x squared negative 1 dx. So this one, we've kind of got to function inside of something else, right? And as of right now, I've not taught you how to do any of this. And I'm not going to today. So there has to be another way to do this problem. No, because it'd be like, if that was an x squared, if it was squared on the outside, I couldn't do the 20 until I did the squared, right? So somehow we've got that negative 1 there that's kind of screwing that part up. Okay, flip back to your phones, look at the pictures you all took of the screen that had all the derivatives on it, or the integrals on it. One of them might look similar to this. Which one? This one?
Oh, never mind.
That. So we have that 1 over 1 plus x squared. And if we look at the problem that we're doing right now, what's the negative 1 do? This is the same thing as saying 20 1 over 1 plus x squared dx. So this becomes 20 arctangent of x. So for those of you who didn't take the picture of it, take the picture of it. You're gonna need them. Yeah. All right, we're not done with this problem. So we're going to put it all back together. So f of x is e to the x plus 20 arctan of x plus c. But they gave us a little more information. They told us what an initial value is. They said f of 0 is -2. We can use that to figure out what c is. So I've got this, and f of 0 equals -2. So f of 0, I have e to the 0 plus 20 arctangent of 0 plus c equals -2. So what's e to the 0? 1 plus 20. What's the arctangent of 0? Arctangent goes backwards. So which angle is going to give you a tangent of 0? 0. And yes, and pi. We'll just take the 0. Because tangent is between -pi/2 and pi/2 is the domain for arctangent. So the only value that shows up in there is 0. Otherwise, you have an infinite number of them. So we restrict it to that. Therefore, it's actually a function plus c. So I've got 1 plus c equals -2. So c equals -3. So my final answer is e to the x plus 20 arctangent of x minus 3. Okay? Have I totally blown your minds yet? Good. I have to try harder. All right. So this is the second derivative. Find me my function. So you're going to do your integral twice. But it's a really easy problem. Just, I'll show you. You'll see the. Okay. What happens when it's not? Don't plug in the zero there. Don't do that. Nobody's actually happy yet. Because we're right there. We're the right there. Close. Almost. Really close to sort of our.
Oh.
You're the only one to cut the X though. All right, let's see. So from what I saw, I didn't see anybody screw up the actual bring down the number incorrectly. So that was a good thing. So 12x squared becomes what? Huh? The derivative of 12, or the integral of 12x squared is 4x to the third. Integral of x 6x? 3x squared. Integral of negative 4? Negative 4x. So remember, when you do the derivative of the integral, when you do the integral of a constant, it gains an x. That's important for the next step. Don't forget your plus c. Now we're going to do the derivative, the integral of that, and you're going to catch me saying derivative constantly because in my head. The integral of this. What's the integral of 4x to the third? X to the fourth. Integral of 3x squared. X to the third. Integral of negative 4x. Negative 2x squared. Integral of c. Cx. And we need another letter. So we'll use d. You could use any letter you want. It doesn't make a difference what letter you use. Okay? It really makes no difference which letter you use. They just tend to continue the letters after C. But it really doesn't make a difference which letter you use. Just don't use something that could be a constant. Like don't use E, because that kind of means something. So like, but I've seen people use capital E's and stuff like that. I typically would do C, D, and then I would have skipped E and done F, G, and things like that. So this way, there's no issues with that. And they're typically written as capital letters, not lowercase letters, for similar reasons, because lowercase letters are typically your variables. So, all right. So we've got that. So I know f of x is x to the fourth plus x to the third minus 2x squared plus cx plus d. Now, we've got two initial conditions, which will help me find C and D. So the first one, if I plug in 0, I get 0, 0, 0, 0. So D equals 4. Does that make sense? All right, I'll write it out. It's fine. So everything cancels out except D. So D is 4. And we know that now f of 1, 1 to the 4th plus 1 to the 3rd minus 2 times 1 squared plus c times 1 plus 4 equals 1. So I've got 1 plus 1 minus 2 is 0. So I've got c plus 4 equals 1. So c equals -3. So my final answer is 9. I will tell you the vast majority of problems you are going to do in Calc 2 is integration. You will not have initial conditions. You're just going to put plus c at the end. Okay? It is not a common occurrence. However, when you're doing any kind of application style problem, you might have those initial conditions. And that's actually some of the stuff we're going to look at in a minute. The other thing is we're going to learn about 2 different types of integrals. This is known as an indefinite integral that we're doing right now. So an indefinite integral goes on forever. There's no endpoints to it. A definite integral will be written like this with numbers here. So it'll be like the integral from 2 to 5, for example. That's a definite integral. And we're going to actually plug those answers in at the end. And again, we don't have a C in that situation. We're just going to plug those numbers in. We will talk about that in the next couple classes. So no number or no symbol, indefinite. And this is a definite. And I'm probably spelling this wrong, but it's fine. All right. The wonderful word problems. All right. So while most times when you're looking at doing an actual class, in every class, even in algebra and everything else, you're learning the rules how to do it. But there has to be an application for anything. Otherwise, there's no purpose in doing it other than just annoying you. So why do we care about being able to go backwards? Well, in some situations, it is very hard to, like, for example, this one, it's very hard to identify the path a particle is going to take. However, it's pretty easy to be able to monitor its velocity, how fast it's going, because that's a change, or its acceleration. We can monitor those things pretty easily because we can monitor changes, but position's hard. There's a whole concept of, like, in the quantum realm, like you can, if you observe it, you've changed it. So by observing it, you can never observe exactly what's going on at that one instance. So by taking the information that we do know about how things are accelerating or its velocity, we can then find out the position of those objects, which is how they actually figure out where asteroids are or where they're going to be at a specific time down the line. We know how they've moved, we know where they were at certain points, things like that. We can then use that to create an entire path of that asteroid or that planet or whatever else. So in this case, a particle moves in a straight line and has an acceleration given by AT is 6t plus 4. So we know our acceleration is 6t plus 4. They want the position, so they want s of t. So, what is the progression from position to acceleration? So that's the second derivative, right? And velocity is the one in between, right? So this is really the second derivative of the position. My velocity is the first derivative of the position. And then, of course, I have s of t. All right, so find me my, since we're going the other direction, we're looking for integrals. So find me my integral of 6t plus 4. This one should be very simple. Right? What did they give us any information about its velocity? So its initial velocity is -6 centimeters squared, or centimeters per second. So if I plug 0 into my velocity, I would get -6, and I also be able to find c. So what's c going to be? -6. Okay, find my integral again. All right, and we also know the initial displacement, right? Is 9 centimeters, so that would again be c. So there's my position function.
The velocity, the initial velocity has to be like.
Go backwards. They don't always have to go forward. You're going in reverse. When they're talking about particles, they're talking about literally like particles of light or sound, things like that. So it's like they do crazy things sometimes. So, Yes, you could technically have a negative velocity. All right. I'm going to test your memory skills. Think back to high school or your Algebra 2 class, probably, whenever you took it. Does anybody remember the general form of the equation for a path of a ball? Or even what number it started with? Huh? You did. Hold on. Let's see if I can find one real quick. Finding all the hard ones. Like, really? I want a very simple problem. And I'm literally finding these massively complex problems. Like, I don't have an Algebra 2 book sitting in front of me, so. Just want a simple one. This works. They always start off with negative 16t squared or whatever it is. And in every algebra class that I ever taught, they're like, why? Why is it negative 16? You're going to find out why. All right. So ball's thrown upwards with a speed of 48 feet per second off from the edge of a cliff, 432 feet above the ground. Find its height above the ground t seconds later. So if I throw a ball, as soon as it leaves my hand, what's its acceleration? What's the only thing acting on the ball is gravity, right? What is the gravity or acceleration of gravity? Negative 9.8 meters per second, right? Okay, so negative 9.8 meters per second. Right? Okay, first off, we need this in feet, not meters. So it's 32 feet per second squared is the acceleration based on gravity. I know, it's the annoying Americans with their feet instead of meters. So my acceleration of t is negative 32. What's my velocity of t? Almost t. Okay. Plus c. What's the plus c? Do we have an initial condition for velocity? Plus 48. That's my velocity. That's my initial condition for velocity. So plus 48. Huh? But now What's my position? Negative 16t squared plus 48t plus 432, because we start off 432 feet above the ground. That's where the negative 16 came from. Constant of gravity. And if you did it in meters per second, it would have been 4.9, which is the other number that comes up quite often in these problems, you see, because that's the other piece that a lot of people don't recognize is that the acceleration has to be negative. Okay, because the gravity is pulling on a ball, so it's accelerating in a negative direction, not positive direction. So it's negative. That's where they came up with that equation. The problem is that I couldn't explain that in an Algebra 2 class because you kind of need calculus to do it. So that's where those little things, that always happens. So now, there's 2 more questions to this problem. We've got its height above the ground 2 seconds later. When does it reach its maximum height? We have the derivative. We just need the velocity to be 0, right? So we have the velocity. So we don't have to find the derivative or anything else. We have this. So t equals 48 over 32, which is 6 over 4, 3 over 2, or 1.5. So 1.5 seconds, it reaches its maximum height. When does it hit the ground? When the position equals 0. And how do we solve that? That you did do in your algebra class. That's actually typically the question in the algebra classes. When will the ball hit the ground? You could factoring or the quadratic formula. You typically did this with the quadratic formula because it was too hard to factor a lot of these problems. And what ended up happening was when you did the quadratic formula, you get an answer like this. And I'm not going to make you do it right now. I'm sure if I gave you the formula, you could all do it. If I didn't give you the formula, it might be a little harder because I don't know how many of you remember it. So here's the quadratic formula for those who don't remember it. There's the quadratic formula. So we got 3 plus or minus the 3 squared of 13 over 2. You're going to get 2 answers. Only one of them works. Because the other one's going to be negative. And we can't have negative time. So that's like when you go through, that's the teacher would have talked about. It's like, okay, why can't we have this? And it's like, it's a realistic situation. It's going to be in the ground. In most situations, yes. In most situations, yes, it'll always be the plus version. Depending on how the object is thrown or tossed, it could, it might have actually started at 0, or like I could have done this problem where I'm literally throwing it from the bottom of a pool. And you're looking at where the ground is actually the surface of the pool. Yeah, it's like, where is it going to hit? So like there is other situations where both of them would possibly work. But yes, most situations, it's the plus one. That's the one that works. So it just depends on where the problem is. It's like one of those things like, yes, but. So, but yes, that's how you would do it. And that's why it was always negative 16. All right, so let's do a couple problems. Find me my function. recognize that one of your initial conditions up there is this visited and they're not full. We multiply it by the side. We do side of 2x.
Yeah.
So. Just keep your variable constant, the problem stays. No, as crazy as it sounds, that thing, drive a sign, you put it in like that, it will give it to you wrong, you have no idea why. I was working with a kid with Alex yesterday, and everything she did was right. She typed in X instead of T. I was like, she's like, why is this wrong? And I'm looking, I'm like, nothing's wrong with your work. I'm looking, oh, you put it in X. So it's like those little things can make a difference.
Some of the things right there.
So I will tell you, at the end of these notes, when I post them, are actually some hints on the homework assignments that's in for chapters. We have some. What is that? Okay. All right, let's do it. It's like everything. I don't do these ahead of time. What's the derivative of sine? Cosine, theta. Derivative of cosine? Sine theta. Plus c equals 4. So I've got -1 plus 0 plus c, so c equals 5. So negative cosine theta. Can I do that? Remember, the order doesn't really, in addition to subtraction, as long as the signs stay the same, you can switch them around. You cannot do this. So you will be able to do the integrals. Not yet. There's new rules that you have to learn. So if you look, there's Calc 2. That's Calc 2. That's chapter 7 in Calc 2. So. And so in your case, you would have done the derivative of negative cosine, right? Which is what? Negative sine theta. Right? Backwards. Derivative of sine is negative cosine theta. Plus 5 theta. Plus d. Equals 4. So we have -1 minus 0 plus 0 plus d. Yes. Oh, that's not 3. That's not 4, it's 3. I was like, wait a second, D is not 5. So D is 4. So f of theta is negative cosine. Actually, I'll switch it back for you guys. That's what you guys were about. And don't play an X there. It's a theta. Really easy habit. Always use X's, but it's not always X's. Try this one. Huh? 5,280. I used to do a problem in my trig class when we used to look at arc length and things like that. And we're figuring out how fast, how many rotations a tire does at a certain speed. And we changed it because we had to go back and look at doing unit conversion. So we're like, okay, 60 miles an hour. You think, okay, that's not that bad. 60 miles an hour, I think was it 60 miles an hour turns or 65? 65 miles an hour turns into 88 feet per second. The length of this room is about 40 feet. So doing highway speeds, you're doing the length of this room in half a second. And it's like, it puts into perspective really quickly how fast 65 miles an hour is. Nope. You're off. Oh, I know what you did. I'm almost 9. Yes. Nope. You just did 220 divided by 3. You did the conversion, right? Yeah. Yeah. That's if your deceleration,
I converted
I know you just converted 50 miles an hour into feet per second.
feet and 22 seconds to feet per hour.
Yeah.
And then how many it would take to stop.
Not quite.
Second. Not quite.
Not quite. Well, no, that's quite what you did. Totally what you did. Not quite right. What do we have? So they gave us, when our brakes are hit, that right there is my what? My deceleration. So it's basically, that's the acceleration, right? So A of t is negative 22. Okay. My velocity is what? Just doing the derivative of that, right? Or the integral of that, which is this negative 22t plus c, which is my initial velocity, right? What's my initial velocity? 50 miles per hour, right? So 50 miles, a mile is 5,280. And we divide it by 60 minutes and 60 seconds to change it into feet per second. And we get, so right, did this right, 220 over 3, which is the exact number you came up with. That's 73.3 miles per hour, or 73.3 feet per second.
So is that wrong?
Yeah, that's right. You're off by one step.
Oh, wow.
That's the number you found. So now if I find my position, I now have to take the integral of that. So I get negative 11 t squared plus 220. Yes.
20 over 3 is the that and T. Oh wait, never mind. My bad. I don't have a question.
Okay.
I answered.
We can assume the way this problem's going, because that's my initial velocity, that my initial position is 0. Okay, so we don't need a plus c, because my c would be 0 in this case. All right, so the question is, what is the distance traveled before the car comes to a stop? So which one of these equations that I have would be 0 when the car stops? My velocity. Velocity will be 0 when the car stops, right? So I'm going to set that equation equal to 0. I reduced my fraction. Huh? That's the time. That's how long it takes the car to stop. Correct. We're not done. And one more step. I then put that into S, because that's going to tell me how far it traveled. So, huh? What do you mean we don't have?
It's like, you have the input, like, you know how we have to have the constant?
Right. So that's what I'm saying. The constant we can assume is 0 because we're assuming the car starts when it hits the brakes. So if we say that's 0, they want to know how long it takes the car to stop after they've hit the brakes. So we're going to start at 0 and then determine. So yes, depending on what your initial, like there could be a lot of other stuff before that point, but we're looking at when they hit the brake, that's the initial condition, and the car starts at 0 feet. How far until they've come to a complete stop? So we plug in 10/3 to this problem here. And we get 1100 over 9 or 122 feet. Actually, it's 122.2. So you figured out when you did it, when you got the 73.3 feet, if you took that and figured out how many times that would go into that. So if you divide that by 22, you'd gotten 3.3. Right, you went back, you did the wrong one. So you got actually,
How hard of me.
you got that number.
I do the same thing in chemistry all the time with exponential.
Yeah.
equation and, natural log equation that you can't do this, proportional.
Right. So that's the thing. It's like you got the time. You knew how long it was going to take them to stop, but you didn't have the equation to figure out how far they were actually going to travel.
The answer, because the slower the car starts to travel, the
Right.
quicker it starts to accelerate.
Correct.
No longer
The slower the velocity. Correct. So 122 feet at 50 miles per hour.
That's where my next.
And that's why, like, a lot of times, like, and that's the thing. It's like you sit there and goes, okay, I know how to, I know it, but when you jump, it's like you miss the little pieces, which is important. All right, let's do one more and then I'll let you guys go. Let's do. I want to do a hard one. All right, let's do this one. I like this one. That would be cool. I'm not going to do that. See, I'm going to be nice. I'm not going to give you the really, really hard one that I was just looking at. And before you think, well, that one's hard, this was the one I was going to give you. this one. So what do we got? What's the derivative of cosine of e? Sine v. What's the derivative of 3 over the square root of 1 minus v squared? Arc plus c. That's it. That's how you do 26, by the way. I think if I wrote this step, you might have figured it out. I doubt any of you would have thought to do that.
Oh, wait, so you just make the letter.
Huh? Yeah, so if you have it and then you're going to the derivative, they use it as a capital letter. So, yeah,
Do they ever just show?
not normally. Yeah, typically you always use lowercase letters. So, but that's where, like, this problem is doable with what you know, as long as you can manipulate it using the algebra to get there. I want to see what Symbolab actually, how it does it. Partial fractions. What was it? 2x squared plus 5 over x squared plus 1. So what you'll learn in Calc 2 is you actually have to do long division on that. If you do long division on it, you go directly to that. But I don't think any of you would have remembered how to do long division. Remember the quadratic, the integrals, like when you're taking the number, you have to have what with functions? Yeah. It's funny. So one of the very first lessons I teach in Calc 2, and I don't know if I think Wolfentine's teaching it, or she does, but it's like I go over how to do long division. I go over how to do systems of equations. Like there's certain things that I go over because I know you haven't done them in a long time, and you will definitely need those. So, like I said, the algebra still comes back to haunt you. Doesn't go away. All right, we're done for the day.
Okay.